you got a fairly good idea at least how to solve a high dimensional thing. I'm not saying from the linear models, nonlinear models, as I said that so far our perception is going from the linear model, and you have to understand from the linear model perspective. But as I said that even many of the other cases, nonlinear, non-parametric network data, you can frame it in this. So of course there would be some assumptions, some of the implications, everybody has to understand this part. But you got the sense that using these classical type of tools with some manipulations, you can have at least some kind of solution. So before that actually we didn't have any idea how to do this part. Alright, so that's why it is very important. Now I will talk a little bit about this lambda selection or S, how the way you will take these things. So typically people do what is called the cross validation. I will come to this point, and some of you might know what is a cross validation. It's a very standard one. If you have the full data set, you first divide into k non-overlapping groups. If you have no idea how to do this thing, you just do k-mean clustering even. That's a standard software you can get. So you get k, you can think about k clusters, non-clusters.
I always do that, but how to choose this k?
So
that is another tuning.
Okay, so good point. We'll talk as a good point, another tuning, but I'll tell you something. But why not I just made this comment? You can criticize, you can challenge me any way. These are all ad hoc procedures. There is no theoretical validity. So in that reason, I do not tell my student do any research on how to choose k, but do some research how to choose lambda without completely new innovative thinking without doing this type of thing. Where, because so far how the way the whole theory is, as if I know this lambda or S, I'm just interchanging these two things. You can see when I'm writing in terms of the plus penalized function, I'm writing in lambda, and when I'm writing in terms of this constant S, but both the things are exactly the role of them are same. It's control the sparsity. But in the whole estimation procedures, what you have assumed that somebody actually controlling this guy S or lambda, and you are getting all these estimate model selections also part. And then whole theory so far is you have the consistency, in some cases asymptotic normality, those type of things you can prove under the assumption that lambda is known. But that's why it is a statistics paper. But in ideally lambda is actually not known. So because all of your uncertainty estimation of the parameter, it depends where your lambda is. So now the research has begun both actually computer scientists and we have been doing the same way. Can we have a consistent estimations all simultaneously, lambda as well as the beta? This is a much harder problem. So far there is one paper I have seen in machine learning research, but not much of in statistics journal, because it's a very much complicated thing. So coming back to Professor Dhar's point, how to choose k, generally some choice like k equal to 5 or 10 works well, but there is no theoretical way you can say this is the thing you have to change. So it is much more just for practical algorithm. You divide into k non-overlapping groups, and this part is, as I said, very easy. If you don't like to do by manually, you can just run k-mean clustering and it will give you the k clusters. Then for each cluster k, small k running from 1 to k, fit the model with some known values of lambda. You take a lambda, say for example -2, 2 plus 2. Sorry, not minus. Lambda theoretically has to be bigger than 0. So 0 to 2, 0 to 10, something, some discrete point like 0.2, 0.4, 0.5. In this way, you take a string values of lambda for a given values of lambda, and for a given cluster, you fit the model. And say lambda to the other k minus, for each k, fit the model with parameter lambda to the other k minus 1 group. Okay, what does it mean? That means if I fix this group 1, just set aside that group 1, all the observations. Then I fit the model, whatever the model I am trying for, using the data from the remaining groups. That means if my group size is there are 100 data points, each group size is 10, then I am fitting the model onto 90 observations and 10 observations is remaining there, okay? And you do these things for a number of values of lambda, just not for one values of lambda, for number of values of lambda. Compute the error in the kth part. Now what you will do, once your model is estimated using that 90% of the data, then predict the group 1 which was not used into your model using that estimation from this other data and calculate this estimation error. It's kind of MSE, you can see that. Again, this will be function of lambda because we are calculating only this thing you run provided you know the lambda, because otherwise high dimensional thing would not work. You have to choose lambda such a way.
That one is cardinality of GK, 1 by?
Cardinality of GK. So you calculate this thing, all right? It makes sense. And once again, you have to be very critical here, particularly high dimensional case, because when you are running this thing, you are running that similar algorithm, and this estimate you can obtain only when you are trying to estimate only few parameters which are less than n. So that means your number of parameter when you are estimating, that should be less than 90 if my sample size is 100. So your lambda, when you are, as I said, that you choose all different value, you have to be very careful. You cannot take a value of lambda where there is no penalty, because idea is that you don't like to estimate all of them. Some of them, most of them are 0 already, you know. So that's what it is. Not everything is not automatic. Sometimes I run this thing for this value of lambda did not work, or I got some value, but that means you did not understand what was the role of the lambda. So you calculate this thing, okay? And then you take this, so you do for each of these group 1, group 2, group 3, group 4 for given values of lambda. Then you calculate this quantity called cross validation lambda, that this average of this whole group error, MSE. So if you have 10 groups, that means you get 10 of these things, you take this average this thing. Do this thing for choice for many lambdas, and then choose the one for which this thing would be smallest. Okay? Suggested choice for k is 5 or 10. That's what you will see every book, everywhere. And in my opinion,
No, what is your EK lambda? How will you just go back to the
so
EK lambda is
so in standard case, what would be essentially it would be
lambda you are taking, you are starting with some lambda.
you are starting with always you have to, otherwise your program would not run.
Okay, you will be starting with some lambda.
Yes, and you have to have a sensible lambda such that when your program is running, that in the path many of them would be exactly 0. Otherwise it would not be running. So if someone doesn't have any idea how the algorithm works, he may end up giving you a garbage result because he has no idea how to choose lambda. So actually algorithm is suggesting some way which region or what could be the possible values of lambda, at least certain region. You cannot just choose anything. Okay? So for example, if you take lambda equal to exactly 0, then always you will get all of them are 0. Or if you get lambda equal to too high value, you won't be able to get this beta hat because no way you can get the estimate. Or you get the estimate which is useless, because we know that even p is say smaller than n, but if p is very close to n, your x transpose x inverse is very unstable. So that betas are not really usable, right? Mathematically still it would be okay, but in practice it should not. So that's why you have to have some idea where you're starting for. So once you do these things, yes.
Here, the average will be taken keeping only one lambda constant.
So this exercise you are doing, suppose I took lambda equal to say 0.1.
So it will be constant for all the clusters.
So actually here all the what you did, k minus 1 group, you are fitting one model with all these k minus 1 members.
Yeah.
Like I just said, G1 has 10 members. Then G2, G3, GK all has 90 members. So then you are running this model all these members. Then there is
For one lambda.
for one lambda.
And
Okay.
the average of all.
No, first just do on lambda. Then what you are doing, once you have this beta estimated from these all other groups, you are predicting these guys who are here. So those are these values. So for them you would know the truth. And this was the predicted value for these guys using the other guys. So it's kind of, if you even, yeah, test set. It is essentially G1 here is the kind of the test set. And G2 to GK, all of them are training set. That's what exactly true. So you calculate these things, and you know, if all are different values, then cardinality of GK would be same as this GK. So it doesn't matter. So you do this thing, and then you do, basically this one is a test set, then you change the test set. G2 is your test set, G3 is your test set. As if you are doing, say, this thing for the 20 departments of an institute, if one department is a test set one time, another department is another test, similar concept essentially. It goes like this, okay? Yes? So it's a notation that what does it mean? That means this beta hat has been calculated without the data from this K. So your model is, if your model is good, it should work the data which I did not use for the model, right? So that's what minus K means. This one was used where K thing was not there. It's a model validation. Your model will do always good for the data which you have used for the estimation, because that's the thing you have used. But how good it is, you have to test it, the data which you did not use to fit your model. So that's what essentially it is doing. Okay. So then you do this thing for, this is a test set, then second one test set, third one in this way. So how many times you have to run this part? For a choice of lambda, you have to run K many times. And as I said, that K's choice could be either 5 or 10, depending on the data size, depending on the number of variables, you have to do some manipulation. There is no theoretical way I can say much. And then you calculate for a given lambda, you calculate the average prediction error. So this is nothing but the prediction error. So you can see that essentially what cross-validation control. It essentially minimizes the prediction error, and that's why this process would kind of favor for the problem of prediction rather than estimation. But at this point, I don't like to go too much about it, but you can see that this is the procedure, and you can understand what's going on if you use the cross validation. So if you do this way, and then as I said that you choose, so for a given lambda you get only one value. Although you have 10 groups, you are averaging with all the groups, so you get one value. Then change the lambda value different. Do the same thing again and again and again and again, and look at where it is the lowest. So a typical way here is these things, kind of this plot of this mean square, that's the sum of the all the groups, and I choose these values of different lambda. It is in the log scale, that's what it is, sum of this minus, sum of this plus. If I vary these things, then the mean square error looks like this. And what is the rule? Rule is that you choose that value of lambda for which this guy would be minimum. So it should be much more kind of your subjective choice. As you can see, this curve, mathematically hard to explain this curve, what it is. Like it is a continuous or absolute continuous or anything, it's too difficult to say. You cannot say much. What you essentially do, once you see that it's kind of get flattened right here, typically if your procedure is very good, very robust, you choose any value lambda from here to here. It does not need to be pinned down to exact thing. And again, idea was what? Idea is that you are solving a problem not to give you the exact pin down that 20 gene, rather than you like to have some subset of the gene which will contain 20. So that's, from that perspective also, you don't need to be very pinned down what is called the exact lambda, because there is no exact lambda in such sense. But by doing this way, you can have a sensible lambda. So in such sense, if I choose any value in this region, it should work for the given problem. Make sense? So it's kind of, in my opinion, it's kind of this type of problem you do. If your sample size is very high, whether you are doing n minus p or you are doing 1 over n, what does it matter? If p is small n, it is for the, or mathematics purposes it matter. But in practice, it doesn't matter at all. Right? Say n equal to 20,000, p equal to 20. What does it matter?
You were saying it does not matter, but in BSc third year you used to get this question always. Show that 1 by n minus 1 summation over I equal to 1 to n xi minus xn bar squared.
So
is an unbiased estimator.
our professor even don't know what is the unbiased is. I can bet you that half of the professor cannot explain what is the unbiasedness is. What does it mean in reality?
Once I wrote 1 by n minus 2, somehow I got 0. So I'm saying oh, 1 by n minus p and what I was saying.
So you might say that, okay, you do the mathematics, you will understand what is the difference. But you do here is the data, you do these things, also you see the difference. That's the way my answer would be. What is the difference? You will see this answer. I will give you the data. One time you do this way, one time you do this thing. So look at what the result you get, and then you do the mathematics, what is the difference you get. Then you understand. So that's what the thing. You have to understand what exactly it means along with the mathematics. So cross-validation is clear. This is kind of the so far the most popular technique for selection of the lambda. Yes.
I was wondering for that it is very much possible that I have this function to be near flat for
you mean this cross-validation function?
Yeah, nearly flat for a large range of lambda.
Yes.
So in that case, I mean, as you said that I can take any value of lambda in that range. So if my range becomes quite large.
It might be, but note that what is the idea is, if your lambda is large, right? But if lambda is close and smaller, it's a large value from here to here, but it is lambda scale is changing here. If you are going towards close to 0, that means actually you are making most of them at 0. You have to see that what is the implication of the choice. Although you can take anything, but where do you take? Suppose from here to here it is totally flat, okay? But lambda is close to 0 means I am making most of them at 0. Now given the context, does it make sense? If lambda equal to too high, most of them may not be 0. Is this making too sense? So you then make some balance. Okay? So something like this. So we all do love the asymptotics, but most often we really very few understand what the asymptotic means. Because we all know that n will never be infinite in reality. But really, I still love to have this thing, convergence rate, I try to understand, because that would tell me what should be the properties of, or how the way I will see my answer. That's the understanding. Otherwise, okay, n tends to infinity, that's not the everything. When you transform it to in reality, you have to understand the rate of convergence, etc., which will tell me how much error I'm going to make, how close I will be there. Because in reality, everything is the finite sample size. So same way here, I think, is that answer your question? Makes sense? So because if you understand whole thing, then you also have the idea what actually lambda does. So, and given the context, like a gene context, we know we have to have about 200 out of the 20,000. Then we should choose sensibly that region. But what I'm trying to say, for example, this is a pretty flat, and from here to probably right here, the difference in terms of selection may be from 200 to 210 or 190 to be. What does it matter? When you are targeting around, so when we say that 200, it's kind of around 200 type of things you are looking. So it doesn't matter. So that's what you try to understand oftentimes in terms of the order. That will tell you not the exact number, but where I can be. Okay? Very good. Any other? That's.
So, Arnav, you were trying to say something like that. If you take average of the flat region, suppose flat region is starting from A to B, then we can take our choice. We can propose something like that. Lambda equal to A plus B. That is generally the way we define infimum of x if it's greater than alpha. Definition. You are looking for this
So,
type of definition. That type of very concrete any mathematical formula. I think in
initially
this
I was
case.
thinking that whether this function has unique minimum or not, and because
Anyway, in practice, it is not possible that it is exactly flat. In practice, definitely some deviations will be there. But if it looks like flat, you can take something like infimum and supremum and then take the average, some sort of that. That is up to you.
So it's kind of a practice thing.
It is practice
thing.
Practice,
You do more practice, you will have some idea. But nevertheless, if you have some other idea, there are like sometimes if the likelihood is defined, then we can do GIC type of thing.
Now, for
So-
another case, in the BSc first year, when we learned first time the median for even number of observations, it should be the average of 2 median. But we don't need to consider average of 2 median most. We can consider both of them are median. This is just protocol or literature,
Yes.
the way we follow.
That's true. But there is always a difference between practice and the mathematical correctness. So if you do the practice, it is not really totally different than the mathematical correctness, but it is approximating further. So, and if it helps you to get the solution, then it is better. But so another way I like to say in this way, all depends also, suppose if I don't do all these things, then you do that model validation, say AIC and BIC, but that may be valid only when your likelihood is valid. How do you know that your likelihood is valid? So first thing you question in that thing. If you are comfortable with there, then why not you are comfortable here? Okay, good. So let me just wrap it up this portion. So this is, as I said, that this is the original paper. JRS Series B 1996, there was no mathematics, only proposing this thing and discussion really how it works. The most cited paper in last maybe 50 years, even the most cited paper. After Bootstrap, this is the most cited paper.
Bootstrap 79.
79, so yeah, 40 years. At least statisticians contributed something because all this highly cited thing comes from other people. So this is the one, and I told you there are lots. So this is the list paper, Efron, Johnston, Hesty, Tibshirani. It is in Annals 2004. Okay. Any question? So far you learned actually at least one good thing, right? And as I said, the very powerful thing. So I'll like to spend a little bit more time. I'll coming back. Now, little more here in the computation. I think later on I'll talk about some of the computations. So, if you are really do the practice, my recommendation is try to do this. Annals of Statistics paper actually has all the algorithm written, just like a computer scientist write, it is also written there. So take your one problem, that's the simple data set I gave you. You don't need to do 20,000, just do it by yourself. Then if you do all step by step, really you will understand even much better. And as Subro at the beginning said that how do I know that SCAD, then I would also say that reproduce this one output. And then you will have the idea how difficult this one versus or what is the advantage you get or not. And there is different algorithm which I am not saying, but this is another algorithm. This is also published, maybe Annals, I think, same league guy. And Hunter is also in Penn State. It's called minimization, MMR algorithms. Okay. Basically, Hunter is a numerical mathematics guy, University of Michigan PhD in math department. So this is another algorithm. So some variations, but you can compare those algorithms and see which one you prefer. But in whatever all students said that so far, it's difficult to beat a lot. Lars is the most simplest thing, most stable, and it is easy to implement. And probably I'll show you some steps from the LARS.
Which one? LARS?
Yes.
These steps.
List angle. Yes, sir. Okay. So, just as a continuation, what you do for the, if I do the ridge regression, as I said that ridge regression is also can handle the high dimensional part, but note that it changes instead of absolute values of this thing, it is a square of this part, less than equal to s. Again, if your s equal to infinity, then it does not differ with the least square estimate. But if p is bigger than p is bigger than a, no way you can get this estimate. But this one, but with this restriction, you can get the estimate. And I'll touch base a little bit more, particularly geometrically how it differs from the Lasso. Only one thing so far I said, in terms of the properties also it is different. You can see that because the Lasso is not really differentiable penalty function. And so numerically this would be little easier than this one, because this has a better property. On the other hand, it does not make exactly 0. So it does not have the sparsity type of thing. So in this way, S is not really called the sparsity parameter rather than some tuning parameter. All right. So you have seen exactly how the way Lasso makes some of them exactly 0, but it won't make the 0. So that's why if you have to do the selection, it will not do the work. But if you do the prediction just, then probably you are not interested in selection, then it should be okay. But in my personal opinion, as I said, you have noticed I have been keep saying that although I'm interested in prediction, if I can select some of the variables, even if I do a good prediction, I would understand why I'm making the good prediction. But if there is no selection, then really even if I'm doing a good prediction, I do not know why the good prediction happening. So like when you will classify some people whether credit default or not, you cannot characterize why it is doing if you do the ridge. But if you do the Lasso, you can characterize why a person will be in fault or not fault, how it characterize, because you are selecting as well. Okay. So there are, in last 10 years or so, there are a number of other penalty functions developed in this area. Another highly cited paper, not as cited as Lasso. This is appear also JR series B. So this was your again least square. Then it says two penalty parameter. You have seen both the penalty parameter already. This is L1, this is L2, or this is ridge, this is Lasso. So it's kind of a combinations of the Lasso and the ridge. Typically you choose lambda and 1 minus lambda, like convex combination of this thing, and this is called an elastic net. What is the idea? To understand this thing, why the idea, you have to understand now. Lasso, I told you already that it select and it creates this sparsity. On the other hand, Lasso may not work well if there is a collinearity or the covariates are highly correlated. Then Lasso may not work. In fact, it would not work. Even though you are making some of them 0, but the collinearity might exist even which are not 0, right? Collinearity means you just to have two of the feature vector has to be highly related. That will kill everything. So it is making low signals 0, but it is not doing anything with the multi-collinearity. On the other hand, ridge, why ridge actually econometrician proposed, because in most of the econometric model, econometric setup, variables are highly related, right? As a result, ridge actually work because it essentially invert x transpose x plus something, they add it up, that's the penalty. So in a given situation, you can have both, like multi-collinearity as well as you like to do the sparsity. So idea behind this thing is that one penalty will control the sparsity and another penalty will estimate even there is a multi-collinearity. Everybody is getting my point? So what I said, even if you have this sparsity, still multi-collinearity kill the problem, because among the non-zero covariates, they could be just two of them could be collinear, And if they are collinear, then your program would not go through. The loss algorithm would not go through. But the ridge will go through, because ridge controls this. Ridge can work even under the multicollinearity. So this is a very cute idea. That's why, in my opinion, again, it's a basically Hestes thing, that you combine these two, and then it works well for any situation when you have the high dimensional as well as the important variables might be correlated. Particularly in business sectors, most of the variables are highly correlated. Actually, genes are not that highly correlated. But in socioeconomic things, the variables are much more highly correlated. Like they ask you how much income, how much tax, how much, all these derived type of variables, which are highly related. But in the data set, everything is there. Okay? So as I said, the L1 part generates a sparse model, that's the sparsity. And L2 part removes the limitation of the selected variables and encourages grouping effect, which means that if they are multicollinearity, they are in a same group. So still it works. This is, by the way, Zhao's thesis. And Shubhra, probably you met Zhao. So this is the Stanford guy. So there are, as I said, the literature is now huge, but you don't need to know everything. I'm just, since I have in my note as well, and you need to know there is a variation. So, and what kind of problem you can still solve, because you can identify what has not been solved, and you can propose one. If that is good one, people will buy it.
Is there any literature about because lasso means L1 norm, ridge means L2 norm. Lasso is rhombus constant and ridge is circle constant. But any other shape like whole cube, whole to the power 4, whole to the power 7.
Yeah, LQ, general way called the bridge. LQ, Q could be between 0 to 2. That's the bridge estimation.
Okay, that is called bridge estimation.
That's the bridge estimation. So that concept was there from 1993 from Friedman actually.
Because if you take 3, then it will be something like this one. So,
Oh, well, you have to study, but generally between 0 to 2, because it works.
Because my point is that the way you explained that is possibly, that is Steve Sheeran is also argument something like that. You make the rhombus and the solution space is getting shrinkage and few points are getting to the corner, y-axis in the picture you have seen. So if I take instead of rhombus something like this type of diagram, in that case also solution, some solutions maybe. The ridge and lasso, my point is the main difference is that in the case of lasso, the solution is getting 0. In the ridge, since the solution...
I'll show you. Actually, it will never be 0. It will be small and small, it will never be 0.
But I can take some others.
Yes, you can.
So that the solution, ultimately few solution will converge to the 0.
It is possible. It is possible. Yes, yes. So that's why number of, there are many more even.
Oh, that part of research has been done.
No, you can still, it is going on. People are publishing, but you know, I don't know how much it improvement. So unless it's a really useful differences than the existing thing from the practitioner's perspective, I think I would not be much more interested in. And also, what is my perspective is that still number of theoretical standpoint. If you are really good in theory, if I formulate some of this non-parametric problem in this structure, the theory really does not go through the standard way. And you have to prove some of these things. For example, what is the, already I said that it will solve if a few of them are kind of good signal, most of them are no signal. But few means what few? If I have this much sample size, if I have this much p, then in the order of n and p, can I have a probabilistic bound? Then the solution would go through. Because you can see that whole solution may be blocked. If in truly there are too many high signals, then even it would not work. It's still less than n, but still could be pretty high. It may not work even. So those type of theory would be really helpful when you are particularly developing the computer algorithms. They try to built in the computer programs those type of thing to check whether it have fulfill this type of bound or not. So this actually interact different disciplines research as well. Okay, so let me finish probably this one, something called the adaptive lasso. before I say the adaptive lasso, you again remember that the picture of the lasso and the ridge, as I said, some of them, actually both the cases, it is shrinking towards 0. In lasso case, some of them would be exactly 0, and in ridge case, it won't be 0 but close to 0. So naturally it is not a unbiased estimate like your least square estimate. So you should not use that thing as a true estimate. You can just take it as a detection of the signal, and then you go further. That research, probably that part I won't be able to show you. That is another interest of research, what we have been doing nowadays. We screen down and then we develop the inference procedures, because lasso does not give any inference, it is just detected, okay. So, but it is a biased estimate. So the idea is that you correct some kind of little bit of biasness. So suppose you have some kind of initial estimate, and lasso is essentially this part, right. So instead of solving this one, you are kind of weighted lasso type of things you are solving. And idea is that this will be much more less bias than the just lasso estimate. So that's called that's why it's called the adaptive lasso. Again, this guy made the name out of doing this adaptive lasso. This is a single authorship paper. That's the guy, same guy, the elastic net as I showed you. So again, what is the idea? Idea was that that's why you have to understand really what the estimators are doing, either theory or by practice. We know that lasso really works well in identification, but as an estimate it is not good. So he just corrected by this weighted thing, and then trying to show mathematically that bias get much more improved. But the question is, how do I get this thing? Any idea? Because whole calculation, it is weight means weight is assumed to be known. But how do I know this part? How do I, so if I have to implement this thing, if I don't have this part, you already know how to implement the whole thing, because lasso routine you can run, right? But if you have to run this one, then you have to know another quantity, which is not your data. Data is actually this and this. How do I get this part?
I run lasso.
That is the only way you can do, because particularly in a high dimensional situation, if it is a low dimensional situation, you might do some level of least square thing. You can get this thing. And then you run this constant one to do the model selection, because lasso can be used even for a low dimensional case, which I showed you an example, for the model selection purposes as well. But in a high dimensional case, what you should do, you can run lasso once, get this beta hat, then in the second time you assume that this is known. Now you are running this lasso again. So routine is you are running twice.
So I'm improving this one
over these things. So that's the way algorithm really works well. So that means you really, in terms of computation, you don't need to write another code. You just calling these two code twice with certain adjustment here. Because in the code, in computer code, you have one part this called objective function, one part is the penalty function. In the penalty function, you are changing this thing with some weighted thing.
Each time we are fine tuning.
So it is essentially you are fine tuning second times. Now, this is the algorithm, but in mathematics actually it is a lot more complicated, because what you have to do to find its inference or the bias, you have to first find out the uncertainty bias in the first set, and then conditional on the first stage estimation what is happening in the second stage. Mathematically very challenging thing. This appears in also JASA 2006. So these are, in my opinion, is good idea and good mathematics. I wish I could do some, but I haven't done much. We have done something, but that also appears in Genesis B, because I thought that was a very original idea we did. But everybody is getting my point that we have to really understand the practicality as well as the theory. And theory is a lot more complicated than what we have learned in linear model things. You have to learn a number of different inequalities, all sorts of things. But it's generally works well. So you should not forget this thing. Always I'm trying to impress you by saying this way always you have to think about the computational, this part, the computational thing well developed. So my new method should not be too different from the computational aspect, because who will do the computational thing? Already computational algorithm run by the computer scientists, so that's what I'll use that. But in terms of the statistics property, it is working better. Okay? Probably I'll skip this part. Generally, some of the rules that if you run the Lasso, you should normalize your x vector. Even any kind of variable selection technique, you should try to normalize. I might come back some of these things if I get some time. Some of these asymptotic properties, these are pretty well established, but so like this one is saying, you can see that the consistency rate, how the way it goes, little o square root of n log p in that rate. You can prove for the Lasso and for the all other things, and this gives you some idea how much error you might have. Some of the asymptotic normality, and this is one of the important result. Always I try to. So what is this property is that this is the estimated set, and this is the true set where the coefficients are non-zero. And if you do this Lasso, right, so this is the true set J where this is non-zero. That means true signals are there. And this is the estimated one using certain values of lambda. Now, under certain condition, if lambda has certain properties, you also need many more conditions, like this truth has the sum, it's bounded below, all sorts of things has to happen. If it is there, then probability that your estimated set of the true component, like the signals, goes to the true signals, goes to 1. Actually, right now we have little bit more finer result, like what is the rate, in what rate it is converging to the 1. That is also we can have something. But what I'm trying to make a point is that it would depend on some of the properties of the lambda, because your lambda is choosing. So why you need to know the theory, because as you is already asked, how do I choose the lambda? So if you know this part, it will tell you some of these ideas, because P also you know, N also you know. So it will give you some idea. Although it is not exactly like this, it would be some order of this part. So very naively it is written just for this class. But in theory, you need some of the, like this signal has to be bigger than this thing. As I said that at the very beginning, Lasso will delete all this signal if it is below certain threshold. So that means it will detect only when certain, what is the certain threshold. So there would be some probabilistic bound we can put. Under that probabilistic bound, all these theorems can be provable. Okay? So what's the point of showing this thing without it has all these theoretical foundations, and that's why Lasso is so much popular. And we can, because of the theory we know so much, that's why we can control many things. Why normal distribution is so popular? Because it's not normal distribution is easy. It is easy, but also it is the heavily studied probability distribution. We know in and out of this thing. And that's why we can control but if you use some other distribution, say Lorentz curve or something, we do not know much of the properties. As a result, we cannot control this thing. So that's why it is very much important. If you think that this is the best procedure you are developing, then you need to study this computational aspect, this practical aspects, and all kinds of theoretical aspects, and that theory would help you how to tune your computational part, etc. And theory would tell you how to choose this lambda, etc. Okay? Interesting, right? You guys can start working. But I'll be much more interested to see some of your own problem you are digging in, because some of these things are fairly well established. Okay? Any question? So next half an hour or so, what I'll do, I'll show you a little bit more discussion on ridge regression and Lasso using some simulation study. That's what a couple of our students did, so I'll try to show you. Because as long as you don't do the hands-on thing, you would not understand that much. if I get some time, what I'll try to show you how the way you are framing even a big covariance matrix into this type of problem, but also high dimensional non-parametric regression, how you are framing these things. That part probably I will do it, not the matrix or not the network. Okay? All right. So if there is no question, no discussion, let me move to the next part. So far, so good, right? At least one person here can identify one person. Some of you know the second name. I put that I gave this work to the student who are currently PhD students. Some of you know Sanket, right? I just mentioned to you that Sanket actually from IIT here has the background in computer science. That's what I thought that this project would be good for him. So what I asked him.
He did BTech in CSC and Master in Economics.
So Subdodol. That's what I said, that at least one person know him. So I thought that it would be good background for him. He would be ready. So I wanted to know a little bit more about ridge and lasso in a practical manner first, before even, because as I said, theory we know quite a bit now, but in this process what we also understand, actually we don't know many theory of ridge regression yet. Rather I know a lot more about the lasso because ridge regression was used to estimate, then nobody actually look at this thing. Now it has a different use, so we have to understand what the theoretical properties are. So this was the class project I gave it to them, these two guys. Not guy, one is the girl and this is Sanket. So comparison between ridge and lasso. So basically I asked them to do some simulation and some real data example and just try to understand, have a feeling how these two work. Several times I'm saying that unless you do some your own way, you will not understand what exactly it means. So three different situations, although language is not rightly written. Low signal, high noise doesn't mean that low value of this signal. Low signal, high noise means very few parameters are kind of the significant. Most of the parameters are kind of the zero, that is garbage. Like in the model you have collected lots of data, but most of the data is garbage. So by the way, these are being used actually in many as a cleaning purposes, data cleaning purposes, by cleverly doing some computer programming. Then another one is high signal, high noise means you have large number of high values of beta, large number of values of beta which is zero. That means they are not really at all related. And then kind of the mixed situation. And how does it work, these two, in terms of the prediction, in terms of the estimation. That's the idea to do this project, okay? And I think that those who are interested to learn, so it should be a good one. So go back to the ridge. So this was the ridge penalty function, L2 square, L2 norm. So this is the loss function, least square function, this is the L2 norm. And this one can write it down. You can write explicit expression for beta r hat, r for ridge, x transpose x, lambda IP inverse x transpose y. Note that if p is bigger than n, x transpose x is not invertible, but there is a safeguard here. This the lambda is a safeguard. Because of lambda IP, this is never, since lambda is bigger than 0, this is not a singular matrix at all, so it would be invertible. Although it could be very poorly estimable, but mathematically it is defined. That's why we said the ridge regression works, because mathematically this is fine. When lambda equal to 0, exactly it becomes the least square, so this should be the case. This discussion we don't need to, but in practice essentially what you should do, you need to know that this guy, you definitely, there is nothing called the penalization. So truly that part also already I said, usually you should do the centering. If you do the centering here, if you do the centering here, then you really don't need the beta 0 anymore. And centering usually works better. So actually all these things are done after centering the X matrix. So here is the, remember now contrast the picture from the, although I think they produced this one. So as Subro was mentioning, you can twist depending on the penalty function. This is the true one, least square one. And this is sum of square L2 penalty. So this ball represent the ridge, and then where the ball touches this least square thing, that should be the solution. So the true solution, if we could have done, that could have been here, but because of the shrinkage, the solution becomes here. In this way, this becomes the solution, right? So that's the, but in lasso case, it would be rectangular. But since it is the ball, and this is the ellipse, so it will never be, you will get exactly 0 because it will touch in one point, right? So the same thing is written. So the ellipse and the circle touch, that should be your estimate, blah, 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 blah. So first thing here, as we claim that you are proving that this is not an unbiased estimate. But from the geometry, already I claimed that it won't be unbiased. And here, essentially, you can try to find out how much would be the bias. The bias increases as lambda increases, and that's what we have seen. So lambda, oftentimes, you can treat it as a amount of bias instead of a tuning parameter. That's also you can say, because this is introducing the bias. If there is lambda equal to 0, there is no bias. What's the variance? So variance of these things also, you can say unless lambda equal to 0, the variance does not match. So in general way, the variance expression is this. But to calculate this beta r or variance, you have to invert this matrix. Now think about, although it is not a singular matrix, but if P is very high dimensional, then this is a P by P matrix. This inversion may not work. What is your experience? Anybody, what's the biggest matrix you have inverted in your life? Because there is a reason why I am making this point. What is the biggest matrix you inverted? Not in theory, really in practice.
I did 5 dimension.
Okay. Yes. How about 500?
Even for I am saying about nowadays I don't do computation, but in 2010 even 20 dimension it was difficult in MATLAB 20 dimensional.
And then if you have to do iteratively, you remember that if you have to do the cross validation for one choice of lambda, then 10 groups, you have to do all these things. So
I think Arnav has an experience because he does a lot of computation.
okay, so in any case,
Sometimes metrics come.
But that comes, that is
Oh, sorry.
this is nothing wrong. Even those who are doing computation day and night, very few people do the real matrix inversion in a higher dimensional case. But as Professor Dhar mentioned, that it could be in trouble with 20, 23. You can run your R, there is a code. You put 500, see what's the result it got. And at this point, as I said, that my problem is the million by million dimensional matrix inversion. And there is, yeah, problematic, but we have to do million by million. That's why I couldn't solve the problem yet. We are doing differently. So, but what is the ridge good thing is that, why I'm trying to say that, why also ridge coming to the parallel way. It's not equally popular like Lasso, but it has number of good thing about. It cannot make some of them 0. Actually, you don't need to invert this thing to calculate the ridge. You can do the singular value decompositions. Everybody, I'm pretty sure you know that singular value decomposition. If you follow the singular value decompositions, then essentially you write this ridge regression estimate exactly in this closed form expression, where there is no inversion needed. And that's, from the practitioner's perspective, it's a big thing to think about. and eventually you can predict, because purpose is the, so as I already you can see that this is not a good estimate, and this is truly, once if you are interested on the regression coefficient, you should not do these regressions. But once you have this thing for the prediction purposes, you have the whole vector. This is your, under the linear model, this would be the prediction. You just do simple, these things, everything is coming from your singular value decompositions. You plugged in and you get this prediction very quickly, very fast prediction you can have, even with a 20,000 dimensional predictor variables. So in that way, in fact, it can be even faster than Lasso, because Lasso, I'll show you, it goes iteratively, iterative solutions. But this one is just one time you need singular value decomposition, and once you do this, and singular value decomposition is very fast with this in modern days computing. Once you do this part, then you just use that whole thing here and you get the prediction done. So there is no iteration as such. So that's the beauty of the ridge regression. Probably a little bit more discussion about how to choose the lambda. First thing, as I said, that here also you can do the cross validation, but there is a concept called degrees of freedom control, what is defined again, that this guy is essentially degrees of freedom. But again, from using the singular value decomposition, you really don't need to calculate the inverse. You get this thing done. And what is the degrees of freedom defined? If lambda equal to 0 is 0 sinkage, which gives degrees of freedom is equal to p, that means you are not doing any sinkage. And any value bigger than 0, that will be degrees of freedom would be less than p or so. So as we have talked about, like if I know that I'm looking for about 200 variable which will contribute to my predictions, from here I'll calculate this guy, and then I'll choose the lambda accordingly. So in other words, this would give me, so degrees of freedom, I fix it, say some value 10 or so, I solve this lambda because these guys are coming from your X matrix. I solve this lambda and I get it. So this is another alternative to the cross validation. But I think the second point is that you can alternatively do the cross validation, is often used choosing the lambda. You cannot ask me which one is good, bad, because nothing, again, these are all kind of should work well, but there is no theory that this is better than the other one. But at least my point here to discuss that beside the cross validation, there could be another way to find the lambda as well. So you get to know, you have to define degrees of freedom. Same way in Lasso, which we did not show you, you can define the degrees of freedom, and you can use the degrees of freedom to choose what the lambda would be. Okay, but there again subjectivity is there. It is nothing free completely that everything is automatic. All right. So little bit more of the ridge regression. Forget about the Bayesian formulation, all sorts of things. Now coming back to the Lasso again. Since we have done the Lasso quite a bit, I'll skip this portion and just like wanted to show side by side what the difference is. Here circle touches here, so nothing really is 0, but you can get always a corner, then this would be 0. Like if you go this way, that this one was already 0, the other one is non-zero because of this. So what is this guy? This guy is controlled by your penalty parameter, a penalty function, and this is your objective function. And every case's objective function we are still keeping the same. So by changing the penalty function, depending on your interest, whether you would like to make some of them 0 versus you'd like to do just prediction, you choose this thing, and this is the type of way you can get the idea. But commonality is that in both cases, beta 1, beta 2, getting closer and closer to the 0. And in theory, this will never be exactly 0, but in theory you can prove this one would be, some of them would be 0. Okay? Cross validation I talked already. So now one slide about the Lasso. So remember back that I told you some computational difficulties of the Lasso, and because of this main reason is that this is the L1 penalty. It is not differentiable. But what is it? It is sub-differentiable. So that is the good thing about it. Is not differentiable, but it is sub-differentiable. So using the sub-differentiable, you can define this beta. So what is the advantage is that still beta hat a closed form expression. You remember that if I don't have this thing with the full differentiable way, I have the closed form expression. But with this thing, with the sub-differentiability, I have the expression for the beta hat under this thing. This one is like summation xi yi, this notation, okay? So I think you guys know very well. So this thing. Now I can put everything all together as a solution path, which I can express in this way. All these three equations. So what does it mean? By plot way, it is essentially the solution is lambda difference, and once it is in this region, everything is 0. So basically, beta hat is S lambda xy when this is your solution path. When this guy is in this region, everything is 0. Otherwise, this is the solution goes through this. So what does it mean? If the true values are far away from positive side, you get this should have been the true one. Your estimates are here. So still it is positive. If it is in the negative side, true estimate should have been here, but you are getting this thing lambda apart. But if it is in between here, all are already 0. So that's the beta hat part. So I showed you this one because you can code this thing to solve this beta because it has the closed form expression. And then least angle regressions we already talked about, but I think I'll skip this portion. Rather, you can look at this paper or I can give you this note. But what I wanted to show, yeah, here it will go. So I wanted them to do some simulations, real hand, where I can monitor them what they're doing. So you took a vector that the regression coefficient beta, 15 of them are non-zero, and about 5,000 are 0. And in this case, p equal to 5,000, n equal to 1,000, so p bigger than n again. But what is their low signal means? Not this number, you cannot say this lower because it depends on what is the error is. Because typically, in theory, when we do, we actually put the bound on the ratio of the signal to the noise. That's the way you have to do it. Because noise, or another way, you normalize everything, and then you can work on the signal part. So first thing that simple, all these x's are generated by normal 0, 1. That means I have a x matrix. All of them are normal 0, 1. First of them added up with 1, 1, 1, and all of them, these are, that means garbage piece with my response variables, right? So then certainly you cannot use the least square estimate because p is bigger than n. So you can do the ridge, you can do the Lasso. In terms of the square of the bias, ridge gives it 0.0026. In terms of the Lasso, it gives 4.97 times 10 to the power minus 15. In terms of variance, it is much lower. In terms of the prediction error, it is 16.15, it is 1.256. So theoretically, so what you have seen here, Lasso has a lower test MSE. Lasso selects 22 variables out of the 5,000. That means if you have the 22 variables, and since it is doing the prediction also better, in this situation, you get the prediction error better. That means better prediction. Not only that, you should be able to explain which are doing the prediction. Only these 220 guys are making all kinds of prediction. All other informations I don't need to make this classification or prediction. But here, not only the prediction error is higher, also I don't know which are the variables really controlling the prediction purposes. So in this is one of the classic situation where you can have a clear choice whether you will take Lasso or this thing. But truly, in reality, you also don't know. But it's a kind of, we're trying to understand when it would be better than the others. As I said that in theory still, I cannot say with guarantee that Lasso would be better than ridge, that theory is still, if you can do that theory, you can write a good paper. I can tell you that part. But definitely you have to do authoritatively. So that's the one reason to see this part. So it works well. But is this the case? If that is the case, then we would have said that Lasso is the winner all the time. So let's take the next case. Just a little bit. That explanation already I gave the explanation. But the solution path for these two guys, how the way Ridge works, how the way Lasso works. I think Lasso here, Ridge here. You can see that for the Lasso, certainly guys are coming towards 0. So what is this? You can identify these things are that 15 ones which has the high signal. That's what it took so much to comes to 0. And these are about that another remaining 5,000 variables which are 0 exactly. They right from the beginning very quickly they becomes the 0. Which makes sense because in this case we know the data. But in reality, and here is the cross validation. How does it look like? So why this 2 line? Because you can take lambda from any point here, it will give you similar result. Okay, so that's the cross validation part we already talked about. And this is the Ridge, and you can see that all coming down towards 0, but nothing is 0. It's kind of asymptotically going towards the 0, but it will never be 0. And this is the log lambda by doing this cross validation, mean square error, how does it happen, and then they choose a point here. But here is the very interesting point to see. Typically to find what is the rule, that where it is smallest, right? But if it is still like this monotonic curve, still you might find a lower value, at least visually, but the curve might look like this. So where is the smallest you might find? If you take it here, then probably it should be 0. But if you take 0, then it won't work in practice, because if you put 0, then X transpose X inverse would not work. So you are making basically much more subjective choice. So what I'm trying to say, that lambda could be still practical issue, and you need to be very careful. And that's what theoretically you need to understand, what the lambda's role here, and so that in practice you can implement. Okay? So let's go to the bigger signal. Means again large number of signals are signals. Out of the 5,000, 1,005 instead of 15, it's 100 times more signals, and 3,500 zeros, and still p is bigger than n. In this case, look at this result. What do you see? In terms of the quality of the estimator bias, Lasso has lot more bias. In terms of the variance, Lasso has the higher variance. In terms of the prediction error, higher prediction error. And Lasso choose 151 variables. So if you have large number of signals things, since Lasso has a tendency to delete as much as you can, so it might happen that you are deleting some of the signals as well. Because main idea, again go back, so you can explain why it is happening. Main idea was that if there is a low signal, Lasso will tend to delete, so which means that Lasso will try to detect only few high level of signals. That's what it will try to do that. But on the other hand, Ridge takes care of everybody. He doesn't delete anything. So there is no risk of losing any signal. So certainly Lasso picked, you can see that only 151, but in this case we know there are 1,500 signals are there. So it missed almost 1,350 signals. So how can we expect that Lasso will do good? So it makes sense. Then my question is, do I have any way to make Lasso better? Actually, this is a very good exercise. I don't think that even Sanket understand what it gives you. Because theoretically you cannot say that this is true, that Lasso would be worst or bad. In first case it was good, in second case why it didn't good? I immediately told you that it's missing some of these things because it's selected 151. So but why did I miss? Because you choose lambda too small than what should be, right? But if you do the cross validation has nothing to do with, in theory, what is the number of, so if I say this is a q, this is total number of p, or in other this is qn, q is the q function of sample size, or in some order of the n, some order of the n here. So if I can associate my lambda with the signal strength, number of signal and signal strength, I could have done better here. But the cross validation has nothing to do with how many signals are there and what is the strength of the signals is there in theory. So this is a very good exercise which gives you some feedback how to overcome some of the Lasso problem. Because Lasso is so good, why it didn't work? Because I can clearly see it didn't work because you penalized too much. So that means the issue was not with the Lasso, issue was selecting with the lambda. Because lambda, that's the guy you are controlling. Make sense? So for the same one, just you wanted to look at the path. As usual, it is making completely 0. For the ridge, it didn't. And here, this is also might say you something that this, if you have this type of flatness, selecting lambda can be little more difficult, and as a result, you might lose lot more signals because you tend to make your model much more parsimonious. Rather than in that case, if you have the flat, probably you should go much more liberal, like you like to keep more variable than required even. In that case, your prediction would have been fine. But on the other hand, you are interested in explaining the model, so too much regressor might be not good. So that's what you are running the risk. A lot of things are there. So in any case, what's the whole point is that if cross validation doesn't give you really nice monotonic curve or something, it would be difficult, or I would say not really monotonic. Like if I have like this, would have been easier to detect. But no way you can prove that your cross validation curve would be convex or anything. So in my opinion, this is not really the main issue of the Lasso. It is the associated issue of the Lasso when you are implementing, that many of the implementation part has not been properly theoretically studied. Let's look at the another signal, kind of the mix. So 10 of them are like this, 36 are 0, and much smaller scale, p equal to 50, n equal to 100. So it is not really p bigger than, how come p is bigger than n? It's a typo. So, but just another situation. And what is making these are kind of correlated with this correlation structure is like this. The covariates are correlated, as we talked about already, that if it is correlated, then depending on the correlation, Lasso may not work well. In fact, it won't, if it is high correlation, but ridge will always work. So under this situation, look at this bias and the prediction error. So here still prediction error is low, bias is low. And if you, since this was the case p bigger than, p less than n, you can do the least square as well. For the least square, it is 0.1089, and prediction error is 2.52 something. So what is your conclusion? Lasso is better than ridge. This one probably is even better than least square, but why did it happen? How do you explain this result? because we are trying to explain in each 3 different cases. So one explanation I could do this way. If you have number of correlated variables, then for prediction purposes, you don't need 2 of the same correlated variables, right? You just need 1 of them depending on how much correlation you have. So as a result, this one actually losing some of this power because it is actually selecting only the important one and used for the prediction purposes. As a result, it also has a low bias and it's not losing the prediction power at all. And least square is also doing a little bit similarly, but least square has no penalty, it has lot more parameter. So oftentimes bigger model is not that good. You like to have a smaller model which might have less variability even. So that's what it was in between, and this was, although it works, but for the technical way for the correlated variable it will do the prediction, but you don't need in practice really you don't need too many correlated variables for the prediction of the same guy. Like if I take the math score, probably I don't need the stat score for prediction his outcome because math and stat is very much correlated. So rather by keeping these 2 you might kill the whole process. So that is essentially one of the explanation, but there might be more, and it would be interesting if I can get more theoretical justification. So that is one of the study what we wanted to do to understand how these 2 work in different situations, and that gives you some feedback what to study further. Okay, so it's a good project actually in my opinion. Somebody can write the paper, but I won't because this is but certainly these other work actually gives you some good thought. So you should do some of this project and then get into different data set and see what type of things you'll get. All right, since we don't have, okay, we can spend a little bit time. So one of the real data, again, everybody has the R. This is available, that's what is good thing, Hitter's database. Similar database, I am encouraging you guys to do IPL data. This is not IPL, but this is the baseball. Baseball is kind of the similar to cricket, but it is not exactly cricket, right? Because you have to hit, how many times you hit, how many times the player is playing. So you have to rate the players. And this is a big thing. If you can really rate the player, you can be again millionaire for sure. So there. Yeah, that's what the. In IPL
players play like
baseball. So you guys can get some idea how we are predicting here, and do this one. Nobody has, I think, analyzed the IPL data, right? At least you will get some local TV call that if you are doing something. I'm 100% sure because nobody is looking in a data-oriented way. If you are good in some way, I think you should be able to do it. You don't need to do for everybody, but you can do some of the player study or some of the team study. So it will give you some feedback, but I didn't want to do this thing unless you wanted, you do something, but I assume that nobody has done anything. Anybody downloaded the IPL data? You guys do it. So this would help you. So this is also same way. We wish to predict a baseball player's 1987 annual salary. Here also I think all the players, how much bet would be, right? The similar type of thing. In the opening day, in thousands of dollars on the basis of the various predictors associated with performance in the previous year. I think Subra, what he was trying to mention, IPL player probably get nowadays, IPL player make more money than the basketball player, look like. Although the basketball players were the richest people in the world even. Magic Johnson and other made billion of dollar even. So how to predict this thing? The number of informations are there. For example, number of times at bat in 1986, that season before. Number of hits before, like how many times they hit the ball. Number of, yes, here also you count that. You might do this thing differently. How many times it's a 6 or how many times it's the 4. You have to be a little bit more cricket style thought process has to go. But all these variables are there. the number of home runs in 1986, like hometown versus you are out of the hometown. So because there is difference, right? That's what you always see. Number of runs in 1986. So number of bats versus number of runs. You should look at some of the, because these are different, but again very much related, very much related. Number of walks, number of years in the major league, number of times at bat during his career, number of hits during his career, blah blah. Too many variables, but it's a very nice data set already collected. Number of assists in 1986, new league, a factor with level A and N indicating players league, all sorts of things. And salary informations are there, 59 players data is missing, so they're just deleted. The idea is, how do you predict? So there are some comments, the predictors are highly, this type of study, usually it would happen, even any economic study, the predictors are highly correlated, or any business study. For instance, variables in the number of bat and the number of runs batted, the number of runs and number of walks are highly correlated, and in fact the correlation could be 0.9639. So in general way, it should not work. So you should check the correlation immediately. What is your general idea? How do we detect the correlation? How much correlation you can allow? Do you have any experience, anybody? How do you measure that multicollinearity? Something called the VIF factor. You can calculate the VIF factor. What is, you can Google it, but VIF factor is essentially measure of the correlation, and typically if it is bigger than 10, which means that two predictor variable correlation might be over 90%. So essentially it is, if it is bigger than 10, you should be very careful or delete from this model. So you can see this is the list of the variables and this is the VIF. So number of variables are above 10, which means they are correlated. Okay. So now to fit this thing, again you do this data in a training set and a test set. So with the ratio 2:3, in order to estimate the error of the Lasso and ridge regression, that means you are keeping much more in the test set and keeping low in that training set. But again, you should do whatever you feel like. There is no specific rule that how much you will keep it here. Naturally, the more you have in the test set should be better, but then it will be biased. Oftentimes you will not have that much data. So deliberately here they keep it less number in the training set, more they are predicting. And that's the way you can quickly predict, right? That's the quick prediction would be. And you do this cross validation for lambda. So here is that the best lambda is 211 for ridge regression, which minimum test MSE is not something like this, and Lasso has lambda is 16.78, MSE is this. So this one tells you in terms of the prediction error, again prediction error with the based on the test set. 2 lambda you don't need to know because two different the cross validations, but in terms of the prediction error, which one you see? Which one you will pick? This is the prediction error for the ridge, and this is the prediction error for the Lasso. So Lasso did here only 7 predictors which are chosen by the Lasso. Ridge solution has shrunk, but anyway, so you guys already said that ridge is the better here. Why ridge did better? So in the last example, what I tried to explain that ridge did not do better. The reason was they are correlated, but now it's a correlated variable. Many of them are correlated variable, but ridge again did better. Then why did it do that? So in other words, I'm contradicting myself, right? Why? Again, I don't have the theoretical answer because nobody has the theoretical answer here. So one explanation you can see that it chooses only 7 out of how many, 35 or 22. So if you look at those Ridge and these empirical examples, so when Ridge did better than the Lasso, in which situation Ridge did the better than the Lasso? If you have large number of signals, high number of signals. So here also you are working only how many you said 22. Out of them, even if it detects 7, but Lasso tried to penalize more, so that means number of signal is about 10 or so. So which is pretty much half of the total number of predictor variables. And look back to the empirical study. In that situation, we have seen Ridge did better than the Lasso, because then our explanation was Lasso tried to drop many more variables when your number of signals is too high, because Lasso is looking for really good in this very sparse situation. So in other words, if I have to compare, this problem is little less sparse than where Lasso should work better. Everybody is getting my point? Because Lasso is good, 20,000 to 200 or 20 you are looking for. But 22 to 7, this is not really highly sparse problem. And if it is not highly sparse problem, you really don't get the advantage of the Lasso. Everybody is getting clear? So that is my understanding from both the things, but lot more need to be understandable. So, but all these projects gives you good thought about what should be the remaining thing we should do. So this is one of the good example. You guys can start working with IPL, but now you see that this is not complete because these guys could not explain all this part. So naturally I did not give them the full point. So just for a completion, they put the table like these are the variables are important. So why do we need this thing? If you think that what matters the salary for these players, then next time you would look for those variables, and if you tell the players, they will try to concentrate only those factors so that their market value would be very high. So it would be helpful many ways, because it is how do I concentrate in 22 factors instead of if you tell me concentrate on only 7 factors, it will be much easier. So what I will try to do, I will try to develop a better Lasso model, try to do much more accurately which factors actually making the prediction better, and then I will try to sell. It will be very much usable. But you need lots of data analysis, practice, explanation, validation. It can, but what it is saying that you can actually use this type of technique. Okay, but the data actually what you have is a lot more complete, because this is only one season data. You can have multiple seasons data. Then there could be a number of missing values. All sorts of situations will come in. So it's a big project, in my opinion, and big group should work on that, like 2-3 people. But there could be lots of interesting things you can find. And I'm pretty sure there would be number of people who would be able to fund you if you show that there is a promise that you can find something on your research. Because these are the very catchy thing to do now in today's world. Okay, so it's already noon, but let me touch base one more database, what is called the Khan database. Again, you can dig into R, it is there already. So this is related to the gene expression. Because the previous data was n less than p, but we applied this high dimensional technique. But here really p bigger than n, p is 2308 gene expression measurement. The number of tissue sample corresponding to 4 distinct types of tissue blue cell tumor. So what it is, that means for each one you have 4 different observations. For the same gene you have 4 repeated observations. But number of genes is 2308, and total number of individual is they put 63 X-train contains 2380 gene expression value for the 63 subjects. So training has the 63 subjects and the test has the 20 subjects. So you have to predict whether the cell has the tumor or not. So basically you get the tissue sample from some patient which has the tumor and some patient which doesn't have the tumor. Essentially it is done on the rat. So again, genetic problem. Idea is to determine out of this 2308 which one are significant and which are effective for the prediction purposes, because you would need to classify either one of this group. So they did this again 10-fold cross validation, and we don't need to know about lambda because this is cross validation is there. But what is the MSC? Ridge regression does not allow for variables, so that's we don't need to know. Here you go. For the test set, the ridge and lasso gets 0.419, and for the lasso it is 0.280. So now in this case, lasso is a clear winner. But we can now, what I was trying to explain, I think now I'm consistent very much. You can see that this is a real sparse situation. And in a real sparse situation, even if you are going to do the prediction, lasso does better. And I have the support from this the simulation study, where the real sparse situation only 10 signals where they are 15 signals where they are 1, 1, and about 4,000 somethings were 0, 0, 0, and where we showed that the lasso was doing better. So if it is a really sparse, then lasso should do better in general. Of course, there are a number of, as I said, how good the signal, all sorts of things. But you got now fairly good idea about how the lasso works, how the ridge works, what kind of differences are there, at least in empirically. And in terms of the implementation also, you have seen some of the differences. And I think you got enough about one of the big technique. Again, we did it in terms of the linear regression type, but as I said, that many problems I can transform into this type of setup and then apply the similar technique. So if you understand the whole concept by now, I hope that you at least you did. Actually, you learned a big technique for the big data, one of the big technique for the big data. Fine. So get into one of your data set, that IPL data, and do something. It has lot more. You can see this is just the player individual data, but there would be number of other things like which region, which the manager, which all sorts of things are there, which is the coach, all sorts of. But it is doable to do some fairly good prediction. You can do it, but unless you take into account all factors, it will be difficult. It will be difficult. Your margin of error could be very high. So you have number of data sets. You can start working on these things. Should be good. Okay. All right. So yes.
The value of lambda between the range of that MSC.
That is nothing to do with. Oh.
For comparison purpose, the value of lambda is being chosen between the range of the MSC is observed.
No. So basically, lambda not really between the MSC. You calculate the MSC using cross validation, but then you calculate the MSC for all different choice of lambda. You just check different choice of lambda. And how to take different choice of lambda? Sometimes I showed you at least one case. It would be greater than log p over n something. But generally you take some between 0 to 2 or something. Okay. Say you take 10 values and then draw the curve of the MSC and see where it is the lowest, and go for that. That could be starting point. But then you can keep refining, etc. So this is just the heuristic procedures, and in reality you may have to do multiple times, or you have to redo the things, all sorts of things. It might be doable. But idea is that you calculate, yes, MSC, but for different values of lambda, and then look at where it is the smallest. That's the idea. Okay. think through all these things. PLS, I would say that you should talk about PLS. You have done the PLS, right? You have something on the PLS and the PS, but let's see. I guess we have to now optimize what else, because this is one of the big technique I already talked about. There are many variations, many things we can keep talking about just on this topic, but I think, as you said, that now I'll go a little bit more on the nonlinear model and then the relation with the even machine like neural net, how the nonlinear regression is related, and then probably, oh, we have to do this classification a little bit, right? So number of things are there, but should be good. But tomorrow afternoon we'll spend more time on the discussion. I think that what you guys think, how does it help you, what you are now looking for, and how we can help you in future as well. So I think that's better instead of just lecturing all these things. That would be tomorrow afternoon, but until tomorrow morning we have to spend some time as well. And I and Shubhra will talk that what we will be doing for the next few hours. But tomorrow, this afternoon, no, next few hours means today is fixed. Tomorrow I think I have to optimize something. But anyway, in the afternoon we'll start with.
I will discuss some. First of all, what I discussed yesterday, that Malaria-Watson non-parametric variable selection. I have something in my mind, and then I will discuss about something about the mathematical part of the functional.
Okay.
A little bit, just like.
Because we'll do the classification, and then he would do that functional classification. And in classification, I'll start with small dimensional classification. Then, if you have the high dimensional data, how do you do the classification? But I'll just touch base. Okay. And then, if I get the time, I might show you, even if you have high dimensional non-parametric regressions, how do you select using the similar technique. If I get and then the starting point of the brain image network, spatial data, but these are all current things. So I think I like to rather think, listen about some of the other problems from you guys, so that I can learn something. What are the good problems might be? Okay, that's the idea, right? For the workshop, we have to also learn something. And actually, through the discussion, always we learn. That's the way the whole thing is much more enjoyable.
Okay.
Okay, so
It is 12:20, so we'll come back again.